are like doing two very different things, right? If you increase the like a typical kernel size that we normally use is 3 by 3, right? But if you increase it, what it will do is it will take into account a bigger set. It increases the local dependency that you're looking at, right? If you're looking at 3 by 3, you can see that there are only like these 9 pixels that you're looking at, right? Now if you increase it to, let's say, 7 by 7 or something else, for each kernel operation that you're doing, you're looking at a bigger local dependency set, right? It also increases the number of parameters of your module. So you need more data to train, and then it sort of in adds latency to your problem. It essentially makes your training your model more expensive. Now, adding more layers typically leads to your model learning more complex representations. So, like so my rule of thumb is always that if you add more layers, like going deep is always better than going wide. Like it going deep always is able to capture complexities better than going wide. So yeah, if you're adding more layers to your CNNs, your model would be able to learn more complex things. While if you're increasing the kernel size, it is able to like capture local dependencies which are bigger in size. So I hope that answers this question. And then okay, I think I've answered this training accuracy. Look at this one. Let's see. Okay. Then I see this question by Shreyas, which says, for deep learning, which framework to choose from PyTorch and TensorFlow, and which framework is more generally used in the industry? Okay, cool. It's an interesting question, Shreyas. Yeah, I think if I have to speak from my personal preference, I prefer PyTorch models over TensorFlow models, because TensorFlow models, even though they are faster, lightweight, and everything, but PyTorch models are like the versioning problem. They're more cleaner in a sense that there's backwards compatibility with new versions being introduced and everything. So again, I mean, it's not like you'll get a very big advantage if you choose one over the other. It is you could, like, whichever framework you're comfortable with, you could go with it. It's not going to make a big difference to the problem you're solving. And given that both PyTorch and TensorFlow have a huge documentation available out there, I don't think you'll be losing out if you're actually choosing one over the other. So yeah, it's your personal preference, I would say. But yeah, I am a PyTorch person. So yeah. Okay. Cool. Now after that, I see this question by Rushil, which says, if Adam provide better or good convergence on non-convex deep nets compared with no optimizer? And how should the base learning rate and schedule be chosen in practice? When should one prefer Adam versus SGD with momentum in production? Okay, so first thing first, Adam will always provide you better convergence than having no optimizer in place, right? So let's get that like clear first. And secondly, how should when should one prefer Adam versus SGD, right? So Adam typically leads to a faster convergence, and you don't need to tune your hyperparameters that much when you're using Adam versus SGD, right? You can choose different values of learning rates, or maybe have a bigger learning rate for the first few iterations on for the first few epochs, and then gradually reduce your learning rate, and you could experiment with things as such. If I'm remembering correctly, I think SGD is preferred in CNNs over Adam. But yeah, but like in problems related to NLP, right? Adam is something that is the default out there, right? So that there Adam is preferred. So it's like, if you need fast convergence, if you cannot do a lot of tuning on your learning rate and everything, if that's something you don't need, go for Adam. Otherwise, you can choose SGD, which is like typically done in CNN problems. Okay, cool. Then I see this question by Ravi Shankar Pal, which says, what is the key advantage of using a bidirectional RNN, and what is the main trade-off? Are there any tasks where a bidirectional approach would be inappropriate or impossible to use? So yeah, yes, Ravi, there are. tasks where using a bidirectional RNN would be possible to use. So what are the main key? Let's talk about the comparison between the two, right? So a bidirectional RNN would essentially like look at the context in both the directions, right? Both forward and backward. So it increases the number of parameters, it makes training more expensive, would require more data and everything, but it is able to like learn from your data better because you're looking at both forward and backward, right? But are there tasks where this approach is impossible? Yes, obviously. So now think about if you're generating a sentence, right? Then or like you're doing the text generation thing. There using bidirect like having this bidirectional approach would not make sense because like you do not have any forward data to look at. So like it becomes impossible to use. So yeah, I mean there are a lot of tasks where you cannot do it, but if you can afford to do it, it is like it will learn better, but it's also more expensive to train. So yeah. Okay. Now, okay. Then I see this question by Vedant, which is for large scale e-commerce tasks. How do you decide when to increase network depth versus width to improve performance? I think I briefly covered this question in one of my previous answers. But yeah, increasing your network depth, like I said before, right? Increasing your network depth allows your models to learn more complex, allows your model to learn more complex tasks. So because you're introducing a lot of non-linearity in your models, right? So yeah, and like my rule of thumb, whenever I go for it, I choose to like if my model is let's say not doing better, I try and if my data allows it, right? If I have enough data, I try and go for increasing the network depth and see how my model performs. But then if you think about it, right, there is one con to this thing as well, where you guys must have heard about like learned about this problem of vanishing gradients in your lectures, right? So if you're as and when you increase the network depth of your networks, you might encounter that problem, like that risk increases if your network depth is super high. So that is something you should keep in mind. And I think in CNNs you introduce skip connections for this like to mitigate this problem as well, right? So yeah, I mean it's you experiment with these things, and yeah, with experience you get to know what situation to do, in which situation you can do what. Okay, and then Vedant has like more questions in this one only. Um, how does Amazon approach the trade-off between model complexity and inference latency for real-time applications? Yeah, so I mean, if you have like let's say product recommendations, right? If you have any online models, you actually cannot afford to have very heavy models out there because like the latency would be high. Then it will take a lot of time for your model to predict, and that degrades customer experience, which is something that Amazon is very much against it, right? Customer experience is valued a lot. So like using very large weight models with like billion parameters and all is not something we usually prefer to do in online settings. So if you have any real time model, we always choose to go for a lightweight model. But here, like how to make sure the performance is also not compromised. So there are like a lot of techniques, right? You could like have distillation techniques to make sure you're lightweight, like you have a big feature model out there, and then like you can train a smaller model to learn from the teacher model and like have a good performance while making sure latency is not compromised. And then like when you like actually deploy models in a production setting, there are things like caching and things also that you can do. For example, you have a lot of frequently asked queries and things, right? So you could maybe cache the answers to those queries, and so that your model doesn't have to again and again predict like do an inference on those. So that way you're saving cost as well, and your model is able to give predictions faster. So that's one thing that you can do. Okay, cool. Then I see this question on why initialization is required in Optimizer. This is asked by Souvik Ghosh. So Souvik, I'm assuming you mean here like by initialization in optimizers, like, so essentially when you have a model that you have defined, right? Why do we need to initialize those weight matrices and everything? Is I'm assuming that's what you're asking. So yeah, you there are a lot of methods for initializations as well. I'm assuming you all went over it. I mean, if that's not the case, please feel free to put it in the chat if you're not talking about that initialization. But yeah, there are initialization is typically required so that your model can start learning. There are a lot of ways to do that. For example, you could do a random initialization, or there are things like Xavier initialization, or you could like maybe initialize with the Gaussian distribution, or like a lot of things that you can do. And a good initialization is important so that your model does not, get stuck. Like your model can converge, does not get stuck anywhere, or like while training, and it does not suffer from the problem of vanishing gradients. So which is why it's always good to focus a little bit on the initialization method that you're using. Yeah, and here my assumption is that you spoke about you're talking about that initialization topic. So yeah, cool. Then I see. Okay, let me just go through the questions a little bit. Mm. Okay, so there is this how do by this question by Dimple Harjani, which says how do bidirectional RNNs handle the challenge of sequence prediction when future context is not available? So yeah, good question, Dimple. So here, okay, if you I'm assuming you all went over the training process of BERT as well, or how do you train a bidirectional RNN or like any model, right? So if you're looking at both the sides of the context, then you have both the things that like even forward and backward, right? You have everything that you can look at. But if at the time of inference, the future from that token, right? That when that part of the sentence is not available, how do we do it? We just assume that it is masked, and then we continue doing the prediction on that. So essentially, like for a bidirectional RNN, we would assume that the entire future context is masked. That's how we go ahead with that. Okay. Then I see. Okay, let me see. There are a bunch of questions on like what the process is going to be like for this ML summer school for like interviews and everything. So I would suggest you reach out to the organizing team for better answers on this. They would be able to guide you on this one, or like there must be some booklets that would be shared with you on this in emails. Okay. Then there is this question by Rustam Kumar, which says, how could an RNN help in predicting the next item a customer might buy based on their browsing history? Okay, so cool. So Rustam, I mean, this is like, I think you're trying to ask how recommender systems work, or I don't know if you're asking how specifically RNNs are able to solve this problem and not anything else. But let's think about the latter scenario, right, and see how RNNs are able to solve this problem. So RNNs typically, what do? They look at sequential information, right, and then try and predict the next item in the sequence. So RNNs are very good with sequential data. That's what they work with. So let's say while you were training your RNN model, right, there was another, like in your training data set, there was another customer sequence which is sort of similar to yours, where they bought these n set of items, and then like for that particular customer, your RNN saw that after buying these n items, this is the n plus one item that this customer ended up buying. And now comes your purchase sequence, right? Now it would like, so this is something that your RNN has seen before during training, and it will try and so your browsing history would be sort of similar to some example in the training set, so which is why and then like based on the so which is how it will be able to predict how you are going to do it as well, or like it will try and compute the similarity of your browsing sequence with any all the sequences that the RNN has seen in its training data set, and then that is how it's able to generalize on what your like next and probable actions might be. So it's all about how you're training the RNN and how it has seen the data that it previously saw. So that's how recommender systems work in general as well. Okay, cool. So then there is this question by another question by Rustam, which says, why might Amazon use a CNN before an RNN and process? Okay, wait, I lost the question. Yeah, why might Amazon use a CNN before an RNN in processing product videos for automated tagging? Okay, I'm not very clear on what tagging you're talking about here. So Rustam, if you could, maybe elaborate on this question again, like just expand this question once again and send it. So I'm going through the list of questions. When I come across it again, I'll be able to answer this. Okay, cool. Then let's see. How can an RNN improve demand forecasting for Amazon warehouses compared to traditional methods? Okay, so RNNs work on RNNs work on learning sequential data, right? Now, let's say we're talking about demand forecasting. So here you're learning to predict the demand of a particular product at, let's say, weekly or monthly intervals, and there would be like a lot of seasonality in your data as well, right? At some time of the year, maybe the demand of your model might increase by a lot, and on some weeks or months or at some time points it will also dip a lot, right? So essentially it's a sequence that you're trying to predict on. You're learning from the first t and then trying to predict t plus one data point. So RNNs, because they work well with sequential data, which is how they're able to improve demand forecasting. But I'll tell you from my experience, right? I have worked in this problem of demand forecasting, and like one very strong baseline that is sort of hard to beat is tree-based models. So like XGBoost or XGBoost is something that I saw performs really well, right? So like that is also a very good model that you can use for demand forecasting. So I mean, maybe look into that. But RNN can typically, like you intuitively, if you know about how RNNs work, you would assume that they would be able to do well on a demand forecasting problem. Okay, cool. Then let's see. I'm just reading through the questions. Some of them are a little big, so I'm gonna take some time as well. There are okay. How to decide the depth of ANN and number of neurons in each layer given compute. Okay, cool. Yeah, so let's look at this question, right? How to this question was asked by Ashish Singh, which is how to decide the depth of ANN and the number of neurons in each layer given computational constraint and problem complexity. Yeah, okay. So Ashish, good question. A question that comes to your head whenever you're trying to make a model. Um, just you would have a compute constraint there on your machine would have a certain memory in which you need to train your model, and and you want to make sure that you're able to build the best model that you can given the constraints that you have. So how I typically start is first thing is to look at the size of your data, the variance in your data, and like that would sort of give you an idea of the a model you need to build. Is that, and b, you start with like let's say two or three, if it's a simpler problem, right? You normally start with 2 3 hidden layers in your model, and then you see the performance on a validation set, and then maybe increase it to see if it's not doing so well, or maybe decrease it if it seems to be overfitting on your data. So you start from somewhere, and then slowly build on your model while checking the performance on the validation set. So that's how I go with. But I normally start with 2 hidden layers only in my model if it's a simpler problem, which seems to work well. Okay, cool. Then there is this question by Anushka, which says, can you explain the difference between attention and self-attention? Okay, cool. So Anushka, here I'm assuming you. So self-attention is a kind of attention, right? But what I'm assuming is you're talking about the difference between self-attention and cross attention, maybe. So here, And okay, I'm assuming that you all know how attention is calculated, right? You have query, key, and value vectors, and so you know that whole formula as well, right? So the major difference is in self attention, the query, key, and value vectors come from the same sequence, while in cross attention, your query comes from one sequence, and your key and value pairs come from another. So let's take an example, right? Let's say you're doing you're solving a problem of sentiment classification, let's say, right? You're given a paragraph of a customer review, you want to tell whether or not it's positive, not positive, or have like 4 or 5 other classes that you want, or maybe you want to like predict what emotion is there in it, right? Also in here, if you're performing self attention on it, if you're performing self attention on it, your query, key, and value vectors will come from like that particular input sequence only that goes into your model. Your, let's say, you built an encoder based model, so you would have like all the attention will be like the query, key, and value will come from this particular input sequence only. But now let's say you're solving a problem of translation, right? You're translating from Hindi to English or something, right? You've given an input, like you're given an input sequence in Hindi, and you want to translate it to English. In that case, you would build an encoder decoder model for this, right? But in the decoder part, what will happen is your query will probably come from English, and the key and value vectors would be from. So when you have this encoder decoder attention, right, your query and key value would come from the Hindi sequence. So that's what cross attention is called. So you would see that here, like they're coming from two different places. So that's what cross attention is, which I'm assuming you call attention in your question. Okay, cool. Then again, a few questions on how to get access to these presentations and videos. You could redirect these queries to the organizing team. They would be able to help you. Okay, let's see. Some question on QA System Squad 2.0. I'm not entirely sure what this is. Then again, a question on how to decide when to increase depth versus width to improve performance. Yeah, just repeating myself here, increasing depth would help your model learn more complex patterns, but then again, you have this problem of vanishing gradients to think of that you might encounter, right? Then a question by Amala. I hope I pronounced your name correctly. But it says, how does kernel size affect feature extraction in CNNs? So your kernel size essentially like determines what is the local dependency set that you're looking at, the neighborhood around a particular pixel you're looking at when you're like, you know, so the kernel size determines that. If you increase the kernel size, you would just essentially increase the the neighborhood that you would be looking at, and so it might or might not degrade your performance. And again, it also increases the number of parameters in your model. Okay. Then I see this question by Rohan, which says, how would you handle delayed labels in neural network training without introducing data leakage? Very good question, actually. This is a question that, this is a problem that we do see here, when we're building, like, let's say, recommender systems or trying to figure out which product to target to which customers. The problem of delayed labels is something that you actually see a lot, right? So and you want to make sure that there is no data leakage in your problem as well. So like one of these problems that I worked on, right? So in order to prevent data leak, okay, let's say you build a recommender system, a multi-stage recommender system, right? Where you have a customer, where you want to figure out what is the probability that a customer will end up buying a particular product a customer will end up buying a particular product that they're shown on Amazon. So this was just like your very at a high level the problem that you're trying to solve, right? Now, a few things, right? As soon as a customer, and let's say it's a very high value product here, let's say you're trying to buy a washing machine or a laptop on Amazon, right? Which would cost like upward of 15-20,000 for washing machine. Laptops would go even costlier, right? So it's not something that you would, as soon as you would see, you wouldn't end up buying that product, right? Unless you've done your previous research on it. So I mean, I'm assuming the first click that you would do on this product would come way before you end up buying this. So there is a delay that we see here, which would come into place when like you're trying to predict conversion. So what we typically do is, like, while making the training data for this model, we try and have like an attribution window, where we call it a positive label. If a customer after giving a click ends up buying that product in the next n days or something. So like that's how you make your training data. And okay, now where could data leakage come into place here, right? So you have a customer, you have a product. Obviously, for your model, you would need a way to represent your customer. You would need a way to represent your product, right? Let's say you ended up training a very simple matrix factorization model on it, right? So you don't want, and let's say this particular customer, the inference that you're doing, right? You're doing it on 10th August, right? So you cannot use you cannot use data that came so you're supposed to use the data that is not happening after the click. Like you can, when you're doing matrix factorization, right, what you do is you make this matrix of customer and product interaction. You like put ones and zeros in it, and then you factorize that matrix to make get a customer representation matrix versus an item representation matrix, right? So the data that you're, when you're filling that matrix, you make sure that you're not filling in any data past the click data, past the date of the click, so that your model does not have additional data in comparison to your downstream conversion model. So that's how, like, you just try and make sure that there is no data leakage. You like don't consider data after the click, after the first click or impression, and you have an attribution window to make sure that you're structuring your training data in a way that your model learns how to do that. But then again, there's a lot of work done on delayed prediction, delayed labels, which is something that you could look at on Google Scholar or something. There are a lot of papers out there, so I mean that's something we can look at as well. Okay, cool. Now, what else? Hey, okay, by the way, I do see that Faizan has joined us as well. I think we can, hey Faizan, since we've covered like the first half, maybe we only have like around 30 minutes. Would you like to answer a few questions now?
Sure. Am I audible, Apurva?
Yeah, you're audible.
Awesome. Okay, so I can take the questions starting from the most recent ones. Let me introduce myself. I'm Faizan, and I was the instructor in one of the sessions as well. I think two of them, deep learning as well as in the Gen AI sections. I hope you have seen the videos as well. So I've been working at Amazon since like 7 years now, and really happy to help you guys out here. So let me take the questions starting from the most recent ones, and yeah, let me get started. Okay. So so how can we decide whether to train a CNN from scratch or use transfer learning when working with domain-specific data sets like prod images? This is from Shushti Govere. Okay, so you want to decide whether you can use CNN from scratch. Usually, I would say that you need a lot of training data to like make it work. If you are using it from scratch, it will not work very well if you try to use it with like less amount of data. And also, if there is some data set or some model which has been trained with similar data to your data, then it is better to use a pre-trained model. Like maybe if your data is X-ray images, then you may not find a pre-trained model for it. But if your data is another kind of image classification or some kind of animal detection or vehicle detection, then you will definitely find a lot of pre-trained models for that. So if you can find a pre-trained model for your data for the kind of problem you are using, then definitely start with that. And obviously, if you have a lot of data, like more than 1 million images, then you can still try pre-train. Otherwise, start with I mean, you can try fine-tune, but otherwise always start with a pre-trained model. Okay. Studies have shown that many attention heads can be removed from a trained transformer with little to no loss in performance. Does this suggest that multiple heads are largely learning redundant information? If so, why the models still benefit from having them during training? Okay, in other words, are extra heads form of ensemble backup even if they become dispensable later, and how should this influence our opportunity to pruning multi-head attention models? Okay, so see, the one thing that we do try to do while pruning multi-head attention models is we prune the heads, and that is correct that performance does not dip significantly, but there is still a dip in performance. Okay, and you can get like a very good performance with just a 1 billion parameter model, right? But you will get up to 60% score in a lot of benchmarks like mmlu and all. But if you want to get to that 90% or 80% scores, the really high scores, then you need to have a bigger model and a lot of attention heads. It is definitely one acting as a form of ensemble. Two, it is also helping the model learn very different patterns that it may not have learned with less attention heads. So the attention heads that you are pruning, right? You might be pruning the attention heads that will be used in very fringe cases, but they will still be used somewhere. Now, if you are using the model for very common cases like autocomplete or something, then it will not matter. But if your model is being used for a very fringe case like some coding model which is trying to code in COBOL, right, which is a very old programming language, then pruning those kind of attention heads will hurt your model. So that pruning is not a like a special attention head pruning is not like a very sure shot thing that it will not hurt the model. It depends on the data and the domain. And when you're pruning also, right, you prune actually depending on the data. So you give it a data and you say that based on this data what can be pruned, right? The overall pruning function tries to see that what heads you can prune without having a higher loss on that particular data set. So if your data set is like allowing it to be pruned a lot, then it's specific to your data set, it's not going to be universal, right? ANN and self-attention looked same. Can you clarify more on their comparison and difference between them? So I would say that ANN and self-attention have some difference in the sense that in ANNs, right, you have multiple inputs. They go into the neuron, and there is some weight that is multiplied to the inputs, and then there is an activation, right? That's how ANN works. Now the thing about ANN is that these weights are fixed. Actually, these are not weights which are changeable during the runtime itself. In an ANN, right, the input into weight, the weight is fixed. Now, in self attention, that's not what happens. You actually do routing at runtime, or you do something like you analyze and get the weights at runtime. Because in self attention, what you have is the weights is query multiplied by keys, right? So essentially, you are determining the weight in self attention by multiplying the query and the key vectors, and then at runtime you decide how much that weight is based on qk multiplication, and then take the value vector which is basically the actual input, right? So you can say that if the ANN had the ability to change its weights in the runtime itself based on the input, then it would become self attention. So that is what self attention is, that we are able to change the weights at runtime depending on the input. In RNNs, the cell stores hidden states. What is the mathematical format and structure of the stored information, and how is it used in computation? So I would not go a lot into the mathematical structure, but rather I would say that they have multiple gates, and the way we use them is basically formulated in a way that it works. But truly, I would say that it's not about the mathematics, but rather the neural network being trained that helps it work much better, right? Uh, Sometimes you may need to use the math when you are trying to develop a newer network, like for example RNNs to LSTMs have one extra gate, which is the forget gate, which helps them to also see what to remember, what to forget, right? And GRUs have a different number of gates and a different structure of gates itself, but those were all for computational optimization rather than for the learning ability. Obviously you can train more on a GRU network, so you learn better, but that is aside the point. Move to the next question. uh, Does Amazon, similar to how GGML libraries optimize LLM inference for specific hardware, optimize LLMs for its own hardware? So Amazon has its own hardware stack, and definitely we have some optimization for it. There are also multiple libraries, AutoML and certain other libraries that we are using internally that helps in optimization. But overall, a lot of optimization comes from the PyTorch community as well, wherein compilation of the network and other things do happen through PyTorch itself. So first of all, it would be good to go through the open source optimizations initially, and then you can think of the optimization that are more specific to the hardware stack. Usually, from a hardware perspective, optimizing for a very specific stack means that you will sacrifice generalizability and the ability to port it to other hardware. So that's not the first step we take. We try to use the optimizations that are already available open source. Which optimizers are typically used for training GPT and other transformers? Is Adam AWW preferred for faster convergence, and is SGD still relevant for fine tuning? How is convergence usually determined in these models? So GPT training actually uses very specific optimizers. Adam and Adam W have been used in the general sense, in that you start with Adam or Adam W, and that usually works very well for the problem. But for larger batch sizes, there are specific optimizers that are used, and large batch SGD and some other optimizers are used for massive batch sizes. Adam is not great if your batch size is like 32,000 or something, which is what usually BERT or GPT training goes through. Is SGD still relevant for fine tuning? SGD is still relevant, but a lot of second order optimizers are actually getting way more use nowadays, because these converge faster, and these also do much better without a lot of tuning. SGD is okay if you are training a much smaller network, because if you are training a much smaller network, then SGD might let you tune it much better than what you can tune Adam or Adam W, right? So if you're tuning a smaller network, then do go through SGD. But otherwise, for bigger networks, there are specialized optimizers. How can you please guide how do I implement the papers of different topics on DNN? Hamad Hashmi. Okay, so I think if you're trying to implement a paper end to end, then I would say that it's going to be challenging, because lot of details are usually left out in the paper, like exact hyperparameters used, or what failed actually, right? Usually papers report what succeeded, but what failed is usually left out. So the first step to replicating a paper, I would suggest, is to try to find whether the code is openly available of either the paper or either the preceding works of the paper. Like maybe the code for OpenAI current GPT-5 may not be available, but you will still find code for GPT-2, right? And that from there you can build upon. So first of all, finding code which is available of current work or prior work is important. And the second thing is key, you have to be thorough with the prior work also. Maybe knowing the hyperparameter, getting in touch with the authors, those things actually help. Not that you can just brute force a complete implementation of a recent DNN paper easily. It would take significant effort as well. So if you're taking it up, then do understand that it's a challenging endeavor, and you have to give some energy and effort and time to it to achieve that. Given the rapid advancements in technology, is it foreseeable that we will one day have sufficient computational resources to process 2D, 3D images directly without the need for flattening? 2D and 3D images, I don't think we flatten 2D images, right? Convolutional neural networks do not actually process them flattened. We actually process them in the 2D shape only. The convolution moves in 2 dimensions. And when you talk about 3D images also, like maybe you are talking about CT scans or something which are in 3D. So those ones also we don't actually flatten. We use 3D convolutions for them, where the convolution kernel itself is a three-dimensional cube, like a Rubik's cube, right? So, in fact, if you have a 3x3x3 kind of convolutional window, then it is going to look like a Rubik's cube, and it moves in 3 dimension over the overall data image or whatever, right? So. we don't actually flatten these days. We already process the 2D and 3D in 2D and 3D. We don't flatten it. Which optimizers are typically used for training? Okay, this is a repeat, I think. How does the choice of sequence length during training impact the generation performance of RNN model? Sequence length, right? So sequence length is an awesome topic. So if you know, the sequence length of Gemini is 1 million right now, and GPT-5 is 400K. uh, we have kind of gone into sequence length of massive sizes, right? And uh, definitely, when you train on a lower sequence length, you will not get the performance at a higher sequence length. Like if I train a model at sequence length of 512, and then I try to go for a sequence length of 4000, right? So after 512 sequence length, even if I extrapolate and make my positional embeddings try to work that way, they will degrade in performance. So the performance is not going to be good. So what these recent models do, so in short to answer, the generalization performance will be bad. It will not work for longer lengths. Okay. What these recent models do to save compute is that they start training at a sequence length of like 4000. Okay. And 90% of the training is done at sequence length of 4000. Then the last 10% is done at a much larger sequence length. Like uh, GPT or Gemini type models might go for 5%, 90 to 95% at 100K, and then 95% to the 100%, the last 5% of the training at full context length of 400 or 1 million length total, right? So that's how they reduce the compute while still training at a and still enabling the models to do much longer context length. But if you want longer context length, you need to train for it, and at some part of the training you will have to spend that compute. How is positional encoding done? So positional encoding, so first of all, there is an attention lecture as well, and their questions, you might be able to get better answers in that. But to go briefly, you can do positional embedding by directly using an embedding matrix, where you will say for position 1 what is the embedding, position 2 what is the embedding. That is how we did it in models like Roberta, which was in 2018. You can also do sinusoidal position embeddings, which was done in BERT, which uses sine and cosine to uh, have different frequencies and then use those for position encoding. On the other hand, modern position encoding does something called as rotational embeddings, which are used through complex mathematics, right? Complex as in complex number mathematics. So complex numbers, if you rotate them, they come back to the same point, right? So that same logic is used in rotational positional embeddings, and that enables these models to extrapolate as well. So if your model is trained for 64,000 length, sometimes it will work up to 100K or 120K also. So some amount of what do you say, extrapolation does work because of that rotational position embeddings that we use currently. The transformer uses multiple attention heads, each operating in a lower dimensional subspace rather than a single head operating in the full dimension. What is the of the technology right now, and if you are successfully able to do this, you will get a PhD for sure. I hope you do this because I am really looking for a startup which does this so that I can purchase their product. So that's definitely a market. Okay, so all the best. Why we need to use RNN in LMM era? I think you meant LLM era. Why do we need to use RNN in this era? So, see, there are multiple reasons, right? The one reason is compute efficiency. So, RNNs can be smaller or larger, and the attention mechanism is way more compute intensive than RNNs. So, compute efficiency is one. Other than that, I also think that you can use an RNN to generate continuously and indefinitely. While for a attention model, you may not be able to do that. You just have to truncate from the left hand side and keep generating going forward, right? In a window-wise fashion. In an RNN, in an LLM, that will not be possible. That whatever context size is given, you just have to use that much only. You cannot like extend it. So that's also a problem. But mostly I think it's for computational reasons, and the other thing being that you might be able to mix, like RNN is a building block, right? It's not the final product. You are kind of thinking, why do we use some smaller part like that? But it's a building block. Okay, so and LLMs are a final product, they're not a building block. Attention is the building block. So hey, we are out of time. So I'm really happy for talking to you guys, and I hope you build the startup. Whoever was asking about the music thing, I'm pretty excited about it. So we will be going into the next session. Thank you everyone for joining this one. Yeah, thanks. Bye bye. We'll be joining the next session. Bye bye. Okay, Apurva, could you close the session?